Hey folks, in this video we're going to be covering 1.8, which talks about rational functions and zeros. The skills focus for this section is to solve equations and inequalities represented analytically with and without technology, and the learning objective is to determine the zeros of a rational function. We're also going to use these zeros to solve inequalities. For your warm-up, you're going to write an example of a rational function for each of these 4 different scenarios. You should be writing 4 different equations, one for each. You should pause the video, give it a try, and then press play to see how you did. Here are some examples that I wrote. In the first one, a horizontal asymptote of y equals 0. The degree of the polynomial in the denominator should be greater than the degree of your polynomial in your numerator. Number 2, a function that has a horizontal asymptote of y equals 2. Your polynomials should have the same degree, and the leading coefficients of the polynomials should simplify to y equals 2. And number 3, a slant asymptote that is parallel to the line y equals -4. The polynomial in your numerator should be 1 degree bigger than your polynomial in your denominator, and the ratio of those leading coefficients should simplify to -4. In the last one, the polynomial in the numerator should have a bigger degree than the polynomial in the denominator, and the difference in degrees should be greater than 1. These are just some examples. There are many different examples that you could write for each of them. So in thinking about the graphs of rational functions and looking at these examples, there are many different characteristics that we're going to want to analyze. You could take a moment to kind of look at these 4 different examples and notice some unique characteristics of each. You might be thinking about our asymptotes. We have both vertical asymptotes and horizontal asymptotes. We're also going to have intercepts, both x-intercepts and y-intercepts. Sometimes our functions are even going to have holes. We're also going to want to know when our graph exists above or below our asymptotes. Over the next several lessons, we're going to be covering each of these characteristics. First up are the x-intercepts, or the zeros. We're going to let our rational function f of x be defined by the ratio of 2 polynomials, g of x over h of x, where g of x and h of x have no factors in common. That's to say that we've simplified them and we've taken out any common factors. First, thinking about what would happen if our numerator, g of x, was equal to 0, we'd have 0 divided by some number. Okay? 0 divided by anything is 0, which means we would have a y value of 0, or we would have an x-intercept. If h of x was equal to 0, we'd have some number divided by 0, which would not be possible. Right? We would have an undefined value. When we talk about these undefined values, they're going to end up being restrictions in our rational function, because we can't divide by 0. We do not want x to equal the numbers that cause the denominator to equal 0. So first, we're just going to practice finding those zeros and undefined values. Setting our numerator equal to 0 will find us our zeros of our function. So in this first function, f of x, I get a 0 at x equals 2. Setting our denominator equal to 0 is going to help us find our undefined values. And again, these are our restrictions. We don't want the denominator to equal 0. So I get a restriction, an undefined value at x equals -6 and x equals +3. These values were really easy to find when our polynomials in our numerator and denominator were in factored form. When we look at this next rational function g of x, we see that our numerator and our denominator are left in standard form. So the first thing that I'm going to do is go ahead and factor those polynomials. In my numerator, I have a difference of squares. It's going to factor into x minus 2 times x plus 2. In our denominator, we have a quadratic trinomial. I'm going to look for two numbers that multiply to the end and add to the middle. They are -5 and -5. So this polynomial can be rewritten as x minus 2 times x plus 2 all over x minus 5 squared. For our zeros, I'm going to set those factors in the numerator equal to 0. I get +2 and -2. For the undefined values, I'm going to imagine what would happen if I set that factor in the denominator equal to 0 and I get +5 as my restriction. That would cause an undefined y value. We're going to use those zeros and undefined values to solve rational inequalities. We explored polynomial inequalities in 1.5, and we can utilize some of those same concepts to help us understand more about rational functions. In solving rational inequalities, our first step is going to be to make sure that the inequality has 0 on the other side. We always want to compare it to 0. We're also going to make sure that our function, f of x, is in simplified form, that we have a single rational function, and that it's as simplified as possible. Our third step is to set the numerator equal to 0 to find the zeros and the denominator equal to 0 to find the undefined values. Those are both going to be in our sign chart, just like we did for polynomial inequalities, right? Making sure that we factor if we need to find those values. We're going to create a sign chart with all of the zeros and undefined values. We're going to be careful, though, to make sure that we differentiate between what we put on our sign chart, which of those numbers were zeros versus undefined values, because we're never going to include the undefined values within our solution. Next, we're going to test values within each of our intervals to see if those intervals have positive or negative y values, meaning does the graph exist above or below the x-axis in that interval of the domain. And then finally, we're going to interpret the sign chart to answer the given inequality. So if we have a less than or equal to symbol, we're looking for those negative intervals. If we have greater than or equal to, we're looking for the positive intervals. Okay? Be careful, make sure you write your answer in interval notation, and think about your endpoints. Are you including those zeros or not? All right, we're going to look at a couple examples now. Here we have a rational function. We want to find where that function is greater than or equal to 0. So my first step is to find the zeros and the undefined values. My zeros here, I'm going to set my numerator equal to 0. I get x equals 2. And for my undefined values, I get -6. And +3. I'm going to make a sign chart now with all 3 of those values, making sure I order them. And now I'm going to test each interval. I see I have 4 intervals to test by plugging in an x value in that interval. So for my first interval on the far left, I have to plug in a value that's less than -6. Like -10, for example. Okay, now I'm testing to see if this gives me a positive or a negative y value. I'm not concerned about what exactly that y value is. I'm concerned about the sign of that y value. Is it positive or negative? So I'm just going to do some calculations to figure out the sign. Okay, so if I think about plugging in -10, my numerator is going to be -10 minus 2, which is going to be a negative value. In my denominator, if I plug in -10 into these factors, I would get a negative times a negative. Okay? -10 plus 6 would give me a negative, and -10 minus 3 would give me a negative. Okay? Again, only thinking about the signs, this would give me a negative numerator over a positive denominator, which would end up giving me a negative y value. I'm going to continue this same process for the next 3 intervals. Okay? In my next interval, I'm going to think about plugging in 0. If I plug in 0, my numerator is going to be negative. If I plug in 0 to the factors in the denominator, I'm going to get a positive times a negative value. That would simplify to a negative over a negative, which would lead me to a positive y value. In that third interval, I'm going to think about plugging in 2.5. You can pick any number that fits between 2 and 3. See, if I plug in 2.5, my numerator is going to be positive. In my denominator, I'm going to have a positive times a negative. So that would lead me to have a positive over a negative, which would end up being a negative output. Last interval, pick any number bigger than 3 to plug in. I'm going to plug in 4. If I plug in 4, my numerator would be positive. In my denominator, I'd have a positive times a positive. I'd get a positive over a positive, which would give me a positive output. Now, I'm going to identify my solution by going back to the inequality symbol. I want where my function is greater than or equal to 0. So I'm going to start with the greater than portions, these positive portions, and then I'm going to look for my zeros. I have to be careful not to include the undefined values. My only 0 is positive 2. I'm not going to include the negative 6 or the 3 in my solution because those are the undefined values. So my solution, I'm going to write in interval notation. Would be from negative 6 to 2. Negative 6 is not included. 2 is included because that's my 0, as well as the interval from 3 to infinity. Parentheses on both the 3 and the infinity. In example 2, we have another rational inequality, but this time our polynomials in the numerator and denominator are not factored. So that's going to be my first step. My numerator factors into x minus 2 times x plus 2. My denominator factors into x minus 5 times x minus 5. Okay, now, if you factor your polynomials and you find matching factors, like a factor in the numerator matches a factor in the denominator, you would want to simplify those out. You wanted to divide out any matching factors. My zeros for this polynomial, if I set the numerator factors equal to 0, I get positive 2 and negative 2. For my undefined values, I have a repeated factor, so I'm just going to think about setting that up once. I get positive 5 as my undefined value. On my sign diagram, I'm going to make sure I put these in order, negative 2, 2, and 5. Okay, now I'm going to go through this process of testing values again, one for each interval. I have 4 intervals again, so I need to plug in 4 x values and see if the y value that results is positive or negative. I'm going to start with my first interval, plug in any number less than negative 2. I'm going to use negative 3. Okay, and I'm going to think about the signs of these factors. If I plug in negative 3, I would have a negative times a negative in the numerator. In my denominator, I would have more negatives, negative times a negative. That would simplify to a positive over a positive, which gives me a positive interval. For my second interval, I'm going to plug in 0. If I plug in 0, I would get a negative times a positive in my numerator. In my denominator, I would have a negative times a negative. That would end up with a negative over a positive, which gives me a negative interval. 2 left. In my next interval, I'm going to plug in positive 3. If I plug in positive 3, I would get 2 positive factors in my numerator. In my denominator, I would get 2 negative factors. So that would end up being a positive over a positive, which leads me to a positive interval. Last up, plug in a number bigger than 5. I'm going to plug in 10. In my numerator, both factors would be positive. In my denominator, both factors would be positive. I end up with a positive over a positive, which gives me a positive interval. Now that I've filled out my sign diagram, I'm going to look for the intervals that fit my inequality less than 0. So I just want the negative intervals. There's only one. I don't want my zeros because I'm not including them. It's less than, not less than, or equal to. So for my solution, I just have one interval between -2 and +2. Our last example is going to be solving inequalities again, but this time from a graph instead of an equation. It says the graph of the rational function f is shown in the figure below. Use that graph to solve the following inequalities. Okay, first up I have where this function is less than or equal to 0. So I want all the parts of my graph that have negative y values or zeros. Okay, and I have two pieces of my graph that fit this. The first piece is going to be from -3 to -1. Now I'm not including -3 because that's an asymptote. My graph won't actually reach that x value of -3. I am including -1 because that's a 0. I also have from +2 to 3. Again, +2 is included because that's a 0. 3 is not included because that's an asymptote. When I compare that to the next one, which is where this function is greater than 0, this time I don't want the zeros. I just want the parts of my graph that are above the x-axis. So I have these pieces that are on the far outsides of my vertical asymptotes, and then I have this piece in the middle in between those two x-intercepts, but I don't want to include those x-intercepts. So my first piece on that far left is going to be from -infinity to -3. In the middle, I have -1 to 1, and on the far right, I have +3 to infinity. Parentheses everywhere, because again, I'm not including the vertical asymptotes nor the zeros. All right, for the last portion of this problem, we're looking at where a function is greater than or equal to 1. So we're not comparing it to 0, now we're comparing it to 1. So instead of the x-axis, we're looking at this horizontal asymptote where y equals 1, and we want all the parts of our function that are above it. Those are going to be the two outside portions on the far left and the far right, which in interval notation would be from -infinity to -3, as well as from 3 to infinity. All right, and that wraps up this video for section 1.8. Feel free to rewatch the video as needed and to try some practice problems on your own.